let's jump into catalysts so we have time to get to the lab. Okay, so the last thing that we didn't get to last time is talking about how catalysts affect a rate of reaction. So in the beginning, we said this word catalyst. We said they speed it up. Today we're going to talk a little bit more about how they work and how they speed it up. So catalysts have to do one of two things in order to be a good catalyst. They either, one, increase the number of effective collisions. Now this is key word here. It's not just making more collisions, but actually guaranteeing that they are effective, meaning they turn into product. Right? It's that whole thing how we talked about the keys and the padlocks flying through the air. If the key hits the padlock the wrong way, that's not an effective collision. The other thing a catalyst can do is it can provide a lower activation energy for the process to happen. Now in doing this, what will often happen is a catalyst may add extra steps in a mechanism, but the steps are lower than the other ones. So like in this graph right here, this red line, I know yours is not color-coded, so make sure you understand the difference. The red line signifies the addition of a catalyst. The black line is without. So there's more steps, but they're lower in energy, and so the reaction proceeds faster. The other thing we talked about before with mechanisms, right? One way to identify a catalyst is because it's something you put in, and then it comes back out, right? You can recycle catalysts. You can use them over and over and over again. Okay, so Macy, I'm going to pick on you because I know you were mixing this up last time. In this mechanism right here, what would we classify as our catalyst?
It's the...
I believe in you.
Minus.
Good. Everyone circle I minus.
Yeah.
Woo! Have a smiley face, Macy. So I minus is our catalyst because it got put in and then came out. Now recognize if you had multiple steps, it doesn't have to be very beginning and very end. A catalyst could be introduced like in step 3 and then come out in step 4, and it still classifies as a catalyst. Okay? I'm going to bring up actually a question Nora asked because I think it's good to emphasize here with catalyst. Even though we don't write a catalyst in an overall reaction, catalysts can still be part of rate laws if they're part of that slow step. Right, so catalysts are not like intermediates where you have to substitute them out. You can leave a catalyst in a rate law. Now we have some different types of catalysts. Your books classified them a little bit differently than the AP curriculum does, but there's overlap of what they mean. In your reading yesterday, it talked about homogeneous and heterogeneous catalyst. Really all that means is just like the words say. What does it mean if a solution is homogeneous? It's the same, right? So homogeneous catalyst is a catalyst that's the same like phase or property as what you're doing it in. So it'd be like if a reaction is a solution, then the catalyst is like dissolved in the solution. And that's an example of an enzyme. So an enzyme is a type of homogeneous catalyst. Particularly these type of catalysts bind to the reactant to force its orientation to be the right way. Now, what we don't quite see here in this funny picture that they always show in biology books and things is the whole idea of this active site is the active site has something that draws it to come right there. Otherwise, it's just a game of probability again. So often it deals with like polarity, stuff like that, where there's a charge, and so there's a slight magnetic pole, which is what makes the catalyst effective, right? So it attaches to the catalyst, the reaction proceeds, and then the catalyst is still there at the end. And enzymes for us are just dissolved, or they're just within the solution. That's why they're called homogeneous, right? Like the enzymes, we talked about lactase, right? So lactase is just like in your digestive system, right? So another type of homogeneous catalyst is an acid-base catalyst. And these work through covalently bonding to a substance. Now, for those of you that are going to choose to continue to study science or go into med school or things like that, the next step of chemistry after AP is a class known as organic chemistry. And in organic chemistry, you'll be introduced to mechanisms that are like 20 plus steps long. And they look like these crazy pictures right here. So you don't even know what it means. I just threw one up there just to kind of make you feel like, hey, one day I'll know what that means, and then I'll feel really cool. But the basic idea is still the same, right? So in this case, our catalyst is H+. Okay, so the catalyst latches on to the reactant, causing all these different things to happen, and then in the end, the catalyst comes back off. Yeah?
Is organic chemistry an AP class?
No, they don't have it in high school. Yeah. I've always wanted to do some sort of like intro to organic chemistry, just like, it'd be like just a science elective, but it'd be so fun because organic chem is cool, but no, it's too high up to do in high school, true organic chem, but yeah. Okay, but that's another type of homogeneous catalyst. An example of a heterogeneous catalyst are surface catalyst. So a surface catalyst is where you literally have a surface. In this case, it's saying it's a nickel plate, so it's a piece of metal. And in this reaction, the reactant binds to the surface, helping for the reaction to happen, and then they come back off in the end. And it's called heterogeneous because these are gases, and this is a solid, so that's why it's a heterogeneous catalyst, is just because they're different states, rather than both being gases or both being liquids or something like that. So, but that's the basic idea there.
Does the bond, like the pi or sigma bonds, have anything to do with it? Because the book kind of said it a lot, and I didn't really know.
A lot of times with catalysts is they'll change the bonds in the moment to help them become what they need to become. But that's like not a requirement for it to be there, I guess. But a lot of times it does play a major role in getting the right orientation, is by those changing those double bonds and stuff like that. So yeah, good question. Any other general questions on catalysts? Okay, flip to that paper I passed out today, and let's talk about 5.3. Okay, don't say it out loud, but if you know the answer to this question, raise your hand. Okay, so we have talked about, so far in Unit 5 from the beginning, we have talked about two methods you can use to calculate the rate law for a reaction. By raising hand, can someone tell us what is one method you can use to find the rate law of a reaction? Yeah?
The elementary step,
Good. So if it's an elementary step, then you can just look at the equation and write the rate law, right? Same idea with the mechanism. If you have a mechanism, because they're elementary steps, you can write a rate law. So one method we've talked about is from a given mechanism, you can determine the rate law for a reaction. Now, one of the key things to recognize with a mechanism is it is an experimental thing. It doesn't look experimental because it's not data and numbers, right? But all rate laws go back to experimental data. Okay, good. Have a smiley face for that. Someone remember the other method that we talked about to find a rate law? Yeah, Bonnie.
Using the experimental data and their order.
There you go, good. Yeah, so this is what we did on day 1 with the big tables, where we said, okay, this concentration doubled, the rate doubled, so it tells me it's first order, that type of stuff. So that's another method you can use. Okay, have a smiley face for that, Bonnie. Today we're going to learn a third method, which is graphing data. And by graphing it, we can find the rate law as well. So all three methods are an experimental way to get the same answer. Kind of just depends on your experiment and what you have. And often you'll do more than one to really confirm that your data is accurate.
So does that mean each reaction has their own, like, or like each rate has their own, like, one uses a graph, one uses a table, one uses like a mechanism?
So it should work out for the same reaction that you get the same rate law for all three methods. Does that make sense? So if you had data, a mechanism, and graphing, they should all give you the same answer. If they don't,
Which one you use?
nope. That means something is wrong if they don't all give you the same answer. So great connection though. So with our graphs, here's what we're looking for, okay? We're gonna take our data of concentration versus time, and this is what we'll be doing on Friday in the lab, is we'll gather this data. Well, more kind of what we're doing today, but we'll do it again on Friday in a different way. And then we're gonna graph that data in 3 ways, okay? Depending on which graph ends up being linear, tells you the order of the reaction. Now, first thing you need to recognize with my examples down here, these 3 graphs are 3 separate experiments because they're all linear. When we do it today, only one of them is going to be linear because if the concentration versus time is linear, that means it is 0 order. And yours are slightly different order than mine. I put them wrong on the PowerPoint, so make sure you find the concentration versus time one. Okay, so if that graph is linear, you know it's 0 order. If this graph is linear, that tells you it's first order. So the natural log of the concentration. Now, natural log is a mathematical function. You may have learned it or used it in math. If you don't know what it is, it really doesn't matter because we're just gonna solve for it. So it's just, think of it as just a mathematical process we're going to do, okay? And then this one is for second order. So whichever one ends up being straight tells you the order of the reaction. Okay? Done? Did it work?
Yeah.
Okay, you want to test one more for me?
Okay.
See, I don't know if I have 1 minute. See if there's a 1 molar. I just don't know if it gets, okay. I just don't know how dilute we can go and it still get data. Okay, thanks guys. Okay, so here's an example of a type of question that you can see on an AP test and how you analyze the results. Okay, so the question says, we have the reaction up there. The sample is placed in an evacuated container and the reaction is represented above. The value of pressure is measured and during the reaction and then recorded in the data table below. Okay, so first off, this is the data that was gathered. They measured pressure versus time. Then they took the negative log of that pressure to find this number, and then they took 1 over the pressure to find that number. The question is, what is the reaction order for N2O5? So what we're looking for is we're looking for which graph would be linear. So from data, without taking the time to draw a bunch of graphs, how do I tell if a line is going to be perfectly linear? Eli?
If it's constant, like going through like every single point.
Perfect. Have a smiley face for that. So we're looking for constant change to be linear. So if I look at this data here, is the change constant? No. So it's not this, which means it's not 0 order, because this represents 0 order functions. Okay? This one, if you go from here to here, goes by 0.7, here to here, 0.7, here to here. So what this tells me is the answer is it's first order. Because this graph is for first order. If it was this one, then it would have been second order. Now, that is the one thing that with this you kind of need to have memorized, is you need to know which graph corresponds to which order. So you need to know that concentration is 0, natural log is first, reciprocal is second. The second thing you can find once you know the order of the reaction is you can also then find the value of K. So we have found K before with our big data charts that Bonnie was talking about, but you can also use these graphs to find K. Once you know what order it is, we know the function or the equation of that reaction. Okay? So, since we just found out that last one was first order, we could use this equation to then solve to find K. Now, these equations are on your formula sheet. Okay, they're under the kinetics section. They don't have the 0 order one listed, so if you go to formula sheet, down to kinetics, but that's because 0 order doesn't really do anything, so why would you calculate something for it? Okay, but it does have first order and it does have second order, but it doesn't label them, but they are in order, so. Okay, let's define what these mean. So K is our constant. I'm going to define it here just because it's lower. So K is the rate constant. T is whatever time you're looking at. So K is rate constant, T is time. A, in brackets, what does brackets mean?
Concentration.
Concentration. So this is the concentration of A at that time. So whatever time you're looking at, that's what that value would be. And then A of 0 is the initial concentration. So whatever you started at. So by plugging in these, you can find K. And these would all just be part of your data to begin with. The other thing you can also just do is K is the slope of your line. So you can also just calculate the slope, and you can find it that way. So just reviewing really quick, how do you find the slope of a line? Yeah, so you just do a y minus a y over an x minus an x. Rise over run. Right, making sure these points correlate to each other. Now, sometimes mathematically, you're going to end up with a negative k. K is never negative, so flip it to be positive. So if you ever get a negative number, particularly like with first reactions, you always will, flip it to be positive. Yeah, Eli?
You mean like flip the graph positive, or the graph will stay as...
Oh yeah, don't change the graph, but just change when it says like, what's the value of k? Write a positive number.
Okay.
Good point though, yeah. So don't change your graph, leave the graph as is, but then just switch the sign of your slope.
Okay.
So, questions on that? Last thing here, and then we'll jump into our graphing lab. First order reactions have a cool connection with this thing known as half-life. Half-life is defined as the time it takes for half of a sample to react.
Isn't that only for like radioactive?
It's not only for radioactive things, but it is a big part of a radioactive substance, Macy. Yeah. So when you have a sample that's radioactive, they have half-lives. Often, like, you'll hear about, like, carbon-14. Right? So carbon-14 has a half-life of 5,730-something years. What that means is if I have a 20-gram sample of that, in 5,730 years, I'll have 10 grams left. In another 5,730 years, I'll have 5 grams left. So half-life is the sample continues to cut in half over this constant range of time. The interesting thing with radioactive decay is the half-life will never ever change. It's a difference between nuclear chemistry and normal chemistry. Nuclear processes, we have yet to find ways to control their speed. So when something is radioactive, we can't speed it up, we can't slow it down, we can't stop it, which is why we just bury radioactive waste in the ground. It's because we don't know what else to do with it, or we blast it into space or bury it in the ocean. Right? But chemical processes, we've talked about, you can speed up and slow down, but if it's first order, as long as temperature's not changed, it will continue to stay constant. So first order reactions always have a constant half-life. Second orders do not. Second orders do not have a constant half-life. It will not be this perfect exponential decrease. Same thing with zero order. So it's kind of just a key connection to make. There's a mathematical function that relates the two, and this is also under the kinetic section on your formula sheet. So the equation is T of 1/2. That symbol means half-life. So if you know something is first order, you can find what the half-life of it is by taking 0.693 over K, which is the rate constant again. So if you know it's first order and you have found K, you can find the half-life for the reaction. If it's not first order though, you can't use this equation because first order are the only ones that have constant half-lives. Okay? So for example, just to kind of show you once again the connection, This is another example of an AP type question that I've seen dealing with graphing and half-lives. So it gave us this data, and then it says the reaction is first order. Explain how the data in the table is consistent with a first order reaction. Now, when 1 year my students took this, what a lot of them tried to do is they tried to do what Bonnie was talking about in the beginning. And then they tried to say, okay, well, let's see, this doubled, and then... But the problem is we're missing a key part to be able to do that comparison. You have to have the rate of them to know how it's changing. Okay? This one is giving us the value of half-life. And since half-life is constant, that supports its first order. That's literally the answer. Is since the half-life one didn't change, unless temperature changed, that confirms its first order. Second order wouldn't have that, zero order wouldn't have that either. Only first order reactions have constant half-lives over time.